When you first learnt these, I think in, say, Year 8 or Year 9, come in, grab a sheet. When we first learnt these, I think we distinguished between tree diagrams and probability tree diagrams, even though we used both of them to solve probability questions, right? Does anyone remember what the difference was between tree diagrams and probability tree diagrams?
Was one in your practice?
Yeah, that's right. So tree diagrams are the simpler ones, okay? For instance, if you've got a coin toss situation, right? Maybe 3 coins. Actually, no, we'll just go with 2. It'll take too long. Right? Now, when you toss a coin, okay, there are only 2 outcomes, okay? And we assume, sometimes the questions are paranoid and it says a fair coin, right? A coin that's not in a casino. Both outcomes are equally likely, yeah? So, you can draw out your outcomes like so. Head, tail, head, tail. Okay? Now, this is just a regular tree diagram because every outcome listed is equally likely, okay? One is not more likely than another. So this diagram sort of implies half, 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 right? On every branch of the diagram, okay? But we could just as easily adjust it, right? Suppose you come to my casino and all the coins in my casino are totally loaded, right? And it's twice as likely to get tails than heads. Suppose I tell you that in advance, right? Twice as likely to get tails and heads. So that means that, what are the probabilities for each one? It's twice as likely. 2/3, 1/3, right? So once I put that on there, 2/3, 1/3, to indicate that one branch is more likely than another, this is now a probability tree diagram, okay? And I guess it will continue down this way. Yep. You can see there's the whole setup. Now, more common than a dodgy coin is that, for instance, you've got, I don't know, 3 items in a bag and you reach your hand in and 2 of them are one color and 1 is a different color. Or you can multiply it out as many times as you like. Okay. Now here's the important part. These addition and product rules, what are they about? We'll do them in reverse order actually. The product rule is, for instance, let's say what's the probability of getting 2 heads? Okay? Now, if I want to work out the probability of getting 2 heads, I need to take this one and this one. They're the only 2 ways, the only one way I can get it, by these 2 things happening simultaneously. Okay? Now there's the key word, simultaneously. Since these events are happening both together, okay, I take their probabilities and I multiply them, hence product rule. Okay? So that's why I get 1/3 times 1/3. Again, even though it seems so trivial, okay, don't skip that line. That shows that you get that there's a product happening here. Okay? So there's my probability of that event. Now, the addition rule is where you're trying to get the probabilities of events that are not happening simultaneously. Okay? So for instance, say it's probability of 1 head. Exactly 1 head. Okay? So now what options have I got? Well, there are 2 different ways that this could happen. I could get a head first and then a tail, right? So I could go this way and this way. So there's 1. Or I could go this way, get the tail first and then the head. Now, I'm not rolling a head-tail and a tail-head simultaneously. It's one or the other, okay? So since they're not occurring at the same time, instead of multiplying them, I add them. That's the addition rule. That's all it means. Okay? So in this case, I would say, over this way, take each case one at a time. Often it's helpful to put brackets around them so you can see which event is which. This one will be 1/3 times 2/3. And then I add the other end, because that's what happens, right? Which is in a different order. Again, even though it's trivial, try not to confuse your order here, right? Because these things are actually representing different things. Okay, now, what are we going to end up getting? That's 2/9, and that's 2/9, so I've got 4/9. There's my problem. Okay. Now, these tree diagrams, right? Instead of laying out the sample space in a table, what you've got as a sample space is all the way down the end, okay? So sometimes, depending on the kind of question you get, you might like to find it helpful to actually write out all of the options as soon as you finish drawing the tree. So you might draw head, 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 tail, tail, head, tail, tail, okay? And there, that is my sample space, okay? Now, it's not so useful here because you can't say divide by 4, the total outcomes, because they're not all equally likely. Does that make sense? So that's why we have to pay attention to these fractions. Now, the syllabus says, use this kind of diagram to solve probability questions involving, now I particularly want to focus on this part down here, complementary events. Mutually exclusive events just means what we've been talking about already, that you can't get a head-tail and a tail-head at the same time. They're mutually exclusive. It's one or the other. Complementary events. What are they about? Do you remember? Sorry, that's fine. Complementary events. So the idea of a complementary event is the opposite of something happening. Okay, let me illustrate it for you. Suppose I worked out what's the probability of getting at least one head. So that's different to exactly one head, right? So this includes the option, I can get one head, like here, or I can get 2, right? So either of those are fine. Now, how can we go about solving this? Well, one way of doing it is the same way we approach this. So take all the possible options, head, tail, tail, head, and since I can have at least, I can have 2, so go head, head as well. So there are 3 different outcomes, multiply them through and add them up. Okay, so then I'll get 3 things and I'll take the total. But there's a faster way, right? Instead of taking these 3 and adding them up, if I did this right, all the probabilities of the whole sample space should add up to 1, right? So therefore, what I can do is express this as the probability of at least one head is the probability of something else not happening, namely this outcome down the bottom, right? So the way I can write that is like this. 1 minus this probability, but its complement. So the way that we tend to write that is at least one head, and you put a line over the top, or sometimes you'll see a really long squiggle. Okay? So that means not this happening. Okay, that's why it's 1 minus. Now, another way we can say not at least one head is no heads, right? Isn't that the opposite of at least one head? That means you've got none, okay? And another way of saying that is having 2 tails, okay? Now, do you have to go through this whole rigmarole? No, I'm just putting it there just so you can see the logic that I'm going through. You could probably go straight from this setup to there. I think it's clear that that's the complement of this, okay? And so you need to work out that probability. I'm going to come over here. 1 minus 2/3 times 2/3, okay? And that's 5/9, which is substantially quicker and less error prone than taking all 3 of them and then adding them up. Okay, you wouldn't believe how many problems come up just because people can't add fractions anymore, because I learned that in year 7. I don't need to add fractions. I'm a year 12 student, okay? So pick a method that's less error prone and it's faster. Okay. All right, now I think that's it. Yeah, that's it on the 2-unit probability. So what I've given you, or what you picked up on your way in, has a whole bunch of exercises. Question?
Is there a name for the ones where you put like the cards or like balls in a hat? You take one out, then the denominator also changes.
Hold on. You mean like conditional probability?
No, like you know, like 5 cards, take a card out, and there's 4 cards left in there.
Oh, right. Okay, so with replacement and without replacement. Is that what you're talking about? Yeah, sure. Okay. So, so far I've been dealing with events where your first event doesn't affect your second event, okay? I guess if we take it as your example, suppose now, yeah, these represent 2 different colors and I'm pulling something out of a hat. You just have to be careful with how you write your second branch and the probabilities that are attached to that. So let's just imagine there's 3 objects. One is this and, yeah, it's a coin with 2 heads and a coin with 2 tails or something like that, okay? So, now, let me get a different color since this is a different kind of idea. So if we took it as With replacement, nothing would have changed because you take one out and then you put it back in, you still got 3, okay? But now without replacement, which is your question, well, let's think about what happens. If I've taken a head out and there was 1 to begin with, right? How many will be left? None, so 0, okay? If I've taken out 1 head, then there's 2 things left, right? And both of them will be tails, right? So you can write this as 2 over 2, or you can write it as 1. You can see these 2 events are complements of each other. They should always be complements if they're coming from the same event. Down here, what follows? Well, I took out 1 tail, right? So now there are 2 items left. One's a head, one's a tail. So this will be a half, and this will be a half. And really, that's all the difference. Everything else, your addition rule and your product rule, go exactly the same.